Picture, we got camera, we got audio. Okay, we recorded 4 seconds. Let's see where we are. Let me zoom out. This is assume our spreadsheet when we were last in class. It says Horner, so was this a build-up or a drawdown? You guys are good. What are we going to do tonight? And what kind of test? Drawdown. So do I want to be on this page? Let's look at example 6.4. This looks like a drawdown, right? So I can probably save myself a lot of keystrokes if I start with this page. So let's take 6.4. Oh, there's a Horner. Okay, let's do 6.3. So I'm going to move or copy, create a copy, and move to the end. Okay, so right now my tab says 6.3.2. And I've also opened up 6.7 constant rate drawdown T sub A, which you've all downloaded from the internet, from D2L, right? Let's just strip this pressure time data into a copy of example 3.2. And I can see that I've drawn a line here. Now, I'm going to be real careful because when I copy paste, and if my previous data file is longer, I want to make sure to delete it. And when I paste all my areas grayed, I'm not going to hit enter or click my mouse, but I'm going to scroll down to see when the gray ends. Oh, see, I have more data. Okay, very good. Okay, and 5,000 pounds stayed underlined. That's my initial pressure. Okay, now I'm going to have to do some more things like strip in this stuff. I know that this is 5,000 pounds, but I'm just going to say it's equal to that. Sometimes I go the other way. And why don't you guys tell me what reservoir temperature is by looking at the other spreadsheet?
200 Fahrenheit.
Are you sure? I thought it was 160 or something. Oh, it is 200. Oops. Here I am. It's 200. Okay. You guys read these numbers off to me when I come back over here. Gas gravity. That's boring. How many feet of pay?
60.
Porosity?
10%.
RW?
25 feet.
You know, for some strange reason, I'm using a gas saturation of 100%. I don't think it's given in the text.
Yes, you have to have
Yeah, I have it on my template. I can explain that later if I'm really bored why I'm using 100%. Okay, and what's my gas rate?
3,000.
Okay. Now I'm going to zoom out a little bit and see what I've got over here. So I got time, I got pressure, and I have pseudo pressure. See how I copied that down? And how come? Oh, I see. I don't like it to look curvy like that, so I'm going to get them all to be the same. Are some of these numbers bigger than others? Oh, okay. I got to get it that big for the numbers to look right. I don't think I have anything in column D, so I'm going to get rid of it. And T sub P average, what is that? Produce time average. I think I did that for some kind of derivative. I don't think I need that column at all. And for some reason I don't have any TA stuff. So we don't need a T, that's time produced in hours, that's good, pressure. So what do we need here? What's the next thing I want to calculate? What column do I want to add? Pseudo time. So I usually call that TA. Here we go. And we can do that in one fell swoop, right? What is it called? Pseudo? Pseudo time, and I have a pseudo time that I wrote for drawdown, then I later on wrote a pseudo time for buildup. The only difference between the two is the pseudo time for the drawdown, I'm going to assume the first entry is my initial pressure that I'm going to calculate a viscosity and compressibility at and multiply all my terms so that I get an apparent pseudo time. On a buildup, my first time is not my initial pressure, so I'm prompted for an extra prompt to say what pressure do you want to have those at. Okay. So it's going to ask for 2 arrays. It's going to ask for my time array. And I want to start at 0 because I'm going to capture that 5,000 pounds to calculate my initial pressures at. See, it's going to say T sub 1 is 5,000, and it's going to calculate my pressures at that. Then it needs my gas gravity, 0.6. It needs my reservoir temperature, 200, and it needs my N2 tab CO2 tab H2S. And it's going to build me a whole array, and I highlight where I might want my array to go, starting in my calculated cell, and hit F2, Control Shift Enter. And, oh, you know what I did? I put it in the wrong spot. Let's see. Let's be clever here. I want to undo my array, move my TA up, move this up, and it looks like I'm capturing the array right. I just moved it up. There we go. Then I'm going to repeat that exercise. Highlight the area starting in my cell, F2, which means edit. Edit the cell you're in. Control Shift Enter. And let me have some decimals here. Not that many. Okay, so I can kind of compare. Is this right? I'm surprised it doubled my... See, toward the end of the life it didn't have a large effect. I'm a little surprised. Usually my first time is fairly close. It's twice as much. All right. What is this column? That's my derivative. I like that hurdle derivative I've been doing. For some reason oh yeah, semi-log derivative, it's labeled. Why is it negative? Because it's using pseudo pressure instead of delta pseudo pressure. So I need a column for delta pseudopressure. Delta pseudopressure for a drawdown is the initial pressure, F4, minus my pseudopressure at my time of interest. It's my delta pseudopressure. I wouldn't necessarily have, so my delta pseudopressure, did anybody leave me a marker? I didn't bring my own. Let's just see what I can do here without a blackboard. Try to be creative here. Although I hate to go to PowerPoint because I might lose my image. Okay, there's delta pseudopressure. Now my derivative is not my pseudopressure, but my delta pseudopressure difference divided by the log of the time difference. Now I'll get positive numbers. Okay? And okay, so my original spreadsheet was, for some reason I was doing pressures, and I can get away with just doing pressures on a buildup on my derivative because my pressures are increasing. I was going to draw this on the whiteboard if I had a piece of chalk. But on a drawdown, my pressures are declining. And that's why I got a negative derivative. So I take my delta pressure, my PI minus PWF, and so it increases. So the shape of my type curves have always got to have an increase. So that's why on buildups, where the pressure is increasing, I subtract PWF, and on drawdowns, I subtract the number from, okay, buildups, subtract PWF from the pressure of interest. Drawdowns, subtract the pressure of interest from the initial pressure. So they both have that same shape because they're going in different directions away from. In the case of a buildup, it's going away from PWF. On a drawdown, it's going away from PI. Now what do I got? I got the same thing. Oh, you know, the other thing I got to do here is I'm going to change my times from real times to pseudo times. Okay. All right, and since I'm hurdling 1 over 2, that's why I got a num in my bottom one, because it's trying to grab something below that. All right, I think I'm ready to look at a plot. Let's zoom out. Let's get rid of this. And I'm now ready to get rid of this spreadsheet here. I think I have all my information, right? Oh, I didn't... I don't want the BGs for anything. Only time we ever use BGs is if we use the old oil equations. And sometimes I use them if I'm not given gas gravity to try to match the Z factor and back calculate the gas gravity. And the mu G and CT I was given I'm not going to use because my pseudo time is going to use my correlations. So I'm not going to use any of this other stuff over here. I'm going to close that spreadsheet, and in my spreadsheet I am going to need let's see if this is right. I don't really need this here. That's duplicated. I'm going to delete that. I don't need that. This was a constant from the previous problem. The only thing I don't need B, well, I may need B sub G if I want to calculate gas in place. That's my BG, my mu G at what pressure? 5,000. My CG at all the proper things. And my CT and I'm using 100% gas saturation. I think I'm just using 100% gas saturation so that I can get a little bit closer to the answer in the book, and I think that the book was run with the simulation. They forgot to run a water saturation. I'll zoom out, look for a plot. I'm going to pretend I don't know anything, which isn't hard to do. How come I don't have a graph on this example 632? Do I have no graphs? Is the only thing I did, I don't have a type curve? I didn't do a type curve for this problem? Okay. Yeah. And that was a buildup. Okay, I'm with you. And I didn't do a type curve because there was very few data points. All right. Well, I don't know what I'm looking at here, and I'm going to get rid of it. Let's go over to 6.4 and steal a type curve. Here's a type curve right here. I'm going to copy and paste it. And the last time we did this, we did drawdown, we calculated perm and skin and RWA, and we calculated our T sub D over C sub D, except for I couldn't quite get it done at the right of the answer, and so I put in comment sections that table 6.1 was missing a viscosity term, and hopefully on your own you figure that out. Okay, so let's put our data up here, because I don't know anything about my well. I'm going to pretend I don't know anything about my well. I want to get my data on this type curve, and the only way I can do it is trial and error. Okay, so we're going to make, I don't know what these numbers are. I'm going to insert a column, and I'm going to have, see, this data is coming from the other spreadsheet. I'm going to put my data on here. But I have to multiply it by, I'm going to go grab those column headings right here. I'm going to do strictly trial and error. Okay? I'm going to put in a 1 there and a 1 there. Okay? I have 1, 1. So for my, that's my match point. So what I'm going to really be calculating here is T sub D versus P sub D, because that's, actually it's T sub D over C sub D. And I don't want those subscripted. Okay, T sub D over C sub D and P sub D. I'm going to put my data on this type curve by trial and error. Okay, my dimensionless time, I'm going to of course change this one to get my data to appear, but it's going to be that F4 times my pseudo time, TA. I got to zoom back in here so I can see, everybody can see in the recording. And it's a small number, it's not 0. And my dimensionless pressure is my delta pseudo pressure, and I don't know why we do this, but we multiply by 1 and divide by the other. I do know why, but okay. And we also want a pseudo pressure prime term, which we call the semi-log derivative. And it uses the same multiplier. That's very important. There's not a new multiplier. It's the same multiplier, except for we're dividing, equals. So we take our derivative, which in this first one is going to be a blank, but I started there and I'm going to stick with it. Is already the derivative, and I'm going to divide by this number right here. And that first one is going to be a 0. I'm going to delete it. It's not a valid number, and I'm going to have to delete one at the bottom too. Now we have these big, huge numbers. I'm going to get rid of these pennies. Okay. Now, this X series right here, XY series, I clicked on the pressure derivative. If you look at the bar, it says it's coming from example 6.41, right? Now, I am going to overwrite what it is. Do you see that? The only thing I'm going to leave is the comma 2. See, I've overwritten. You following along? You don't have your computer today? Is it break? Did it break? Okay. I'm a big fan of learning by doing. So I always worry that people can't learn when they're not doing, but everybody has a different learning modality. So all arrays have the name of the array, the X, a comma, the X, a comma, the Y, a comma, and what series it is. So this is I'm going to replace example 6.3, but I'm going to put it in that same place, comma, the X's are T sub D, comma, and the Y's are my P sub D's. And they're going to have left the type curve. See that? Because my 1 and 1 is too far off. But before I make any adjustments, I want to get my derivative series on here. Same way. This is going to say comma 3 at the end. I'm going to save the word derivative, and I'm overwriting from here to here my X, and I'm overwriting here to here. I'm having trouble. My Y, and I'm going to put in my X comma Y. X, and I've already made a mistake, comma Y. And the reason I made a mistake is because there's no derivative for the first point, so I'm going to make that array 1 smaller and that array 1 smaller. Okay, I got my data on my graph, but my trial and error points are so far off, my data doesn't even appear on my graph. So let's try to fumble with our coefficients and get my data on my graph and see if I can make any analysis that will help me move along. Okay, I'm going to zoom out. I'm going to try to get as much okay. My X's look all right. My Y's are huge. So I'm going to divide by this number. Let's try 1,000. My data did not appear. Let's add a 0. Oh, I got to see. Did you see that data appear in the upper left-hand corner? Let's try 10,000. Here's my data coming in. 100,000. Here's my data coming in. And one more 0. I added an O. That wasn't pretty. Okay. I now have my data on my graph. Okay. And incidentally, I used to really like to switch back between PowerPoint and Excel. But do you remember on our last lecture that we had a blue screen for the projector? I'm trying to be as careful as I can so that the recordings are captured. But normally I would tend to copy these. All right, who's ready to make some observations? Yes.
The network of the data seems to be this, the boundary has been achieved. There's some effects of boundary, that's why the curve is very up.
It's up. What happens right before that curve's up? And what curve are you talking about, the blue one or the green one?
The green one.
And what is the green one?
Green one is a derivative.
The derivative curve curves up at the end, and that indicates a boundary. Okay. What happens right before it curves up? Stabilizes. And what does that tell us?
No available storage or upload a radio.
That we have radial flow. Okay? So, where do I want to match that data at?
You can make from the normalization.
I want to match down there at that 0.5. See where all those lines come like this and go 0.5. So I've got to match this data up here down to here. And I'm going to do that with my P sub D. Let's take one more zero. It might be too big. Let's see what happens. It's still not enough, right? Let's try one more, and then I could probably gone too far. So now I'm going to back up. Now I'm going to change my 10 to a 5. Okay. Now, I'm trying to figure out, we're getting ballpark here. We got to get that on that 0.5. That's all we really know. I would say that I have to, what did I do? Let's try 6. I forgot which way I went. Oh, that's too far. That's the wrong way. Let's try 4. Okay, now I have the flat part of my data on P sub D of 0.5. Okay? I'm basically done with my altitude match. You see that? I've diagnosed from my pressure time data derivative that I got radial flow, and that means that those data points right here, after I match it, they call it the level setter because it levels it from top to bottom. And if I look down at my last data point somewhere down here, I should get some. Oh, I'm not even looking at the right numbers. Okay, so in this range right here, let's see, do I have that many 0.5s? 1, 2, 3, 4, 5, 6, 7 points from the bottom. Here's a 1.6, 1.4. Now I want 0.5. Here's a 0.5. Oh, I'm still looking at the wrong numbers. Okay. Let's get a couple more in here. So that's telling me in this 0.44 range to this 0.53 range, that's where I have radial flow. Okay? After I've matched it on there, I'm going to have radial flow there. So I can probably come all the way back here because I'm eventually going to have to grab a time series. And I think this is my time series here. I'm going to highlight those two. So there's my radial flow regime. So even though we were setting up on this problem, being told it was a fractured well, that's going to tell us we're going to have different early time data, but we may have radial flow late. And we did in this example problem. We have some late radial flow. Now, I'm not sure if I can get a better X match, because this is a wellbore storage match. I'm going to play with X, but I am not convinced at this point in time of whether or not I can get a better X match. Oh, that looks pretty good, doesn't it? Okay, we're not going to calculate any properties from our match, but theoretically, at this point in time, we could calculate perm, skin, and wellbore storage. We're not going to do that.
What is your line edge?
Pardon?
Line edge.
I'm sorry, what?
The line edge point. The edge point for the y-axis.
Oh, what would I end up using? 4E8. Okay. When we're done with our analysis, we're going to calculate two numbers in here from the equations, and we'll see how close they are to these. If they're close to these numbers up here, that means we could have gone the other direction and just used those numbers and gotten everything we wanted. Okay. Now we're going to start our lecture on linear flow. I'm going to copy this. I'm going to come over here in the right field and just paste it. And what I'm going to do now is I am going to get rid of the background. Do you see that? I got rid of the background. I got rid of the type curve. There's nothing wrong with that. I am now going to expand my scale so that I get all my data on it. I need a little bit smaller min, and I need a little bit smaller max. I mean y. Okay, now I've got all my data on my plot. I'm going to put my crosshairs on here. I'm going to add major grid lines, and I'm going to play with some slopes. Yeah.
Could I just get you to click on the X, PD and PD prime real quick? I just want to make sure I'm the right.
T sub d over C sub d is my apparent time times my match point. But for my delta pseudo pressure, I divide by my match point. And the reason we do that is because people like numbers bigger than 1. They like match points bigger than 1. And since it doesn't matter if it's oil and I'm using pressure, or if I'm using gas and using pseudo pressure, my delta P's and my delta pseudo pressures are large numbers. In order to get them into the dimensionless time range, I have to divide by a big number. Otherwise, I'd be multiplying by 0.000 something. Yes?
I'm sorry, I apologize if this has already been asked, but why is there a divide by the rates in the description?
I just answered that question. Because engineers like numbers greater than 1.
Sorry.
Okay. Okay, if I multiplied by a number, I would be multiplying by the reciprocal of 4 to the 8th. And again, engineers like numbers greater than 0. So we tend to multiply our time because it's usually a number greater than 1, and we divide by this number because in order to get in our time, our dimensionless time range, we have to make it smaller. So it's easier to divide by a whole number than to multiply. I don't mean a whole number. It's easier to multiply by a number greater than 0 than to multiply by a number less than 0. It's the same operation, but it's easier to display this There's nothing easier. Engineers like numbers greater than 1, rather than real small numbers between 0 and 1. They prefer that number, to look at that number, then it's reciprocal. There's no sense to it. Don't try to overthink it. It's common practice, though.
Well, this is different from build up, right? Build up, we got time this number. For drawdown, we kind of like divide this number, right? Or
No, it should be the same. On a build-up, we multiply by a time match point. Okay, look at the titles up here. It's P sub D divided by delta pseudo pressure match point. This is that ratio. But you see that our dimensionless term is on top of our delta term. Over here we have our delta term on top of our dimensionless term.
I think you might have misunderstood my question.
Okay.
I was asking about column F.
so say if you times the WPP times the coefficient, so it ends up like you got PD, right? I mean, for your case, I think maybe the denominator should change. You know, it should.
I see your point. Okay, let's walk through the logic here. If this is my match point, 2.2, and I want T sub D over C sub D, I see your point. They both should be flipped. Okay, let's just ignore that. This is common practice, is to multiply by time and divide by pressure. Okay? Okay, so we're over here. You guys slowed me down on linear flow. I now have the very first lesson in linear flow. We already reviewed what we already knew about radial flow. Our derivative is, our semi-log derivative is flat during radial flow, and in addition to that, if it goes into radial flow and then curves up, we've seen a boundary. So we've actually got all of our late time data characterized. What's our observation about our early time data?
You get a half slope.
How do you know those are half slope? You actually read the book? You've done this before? Okay. Yes, they're half slope. What I was trying to get you to say, if you had no prior knowledge, is those two lines look parallel. They're both half slope. So this is a very diagnostic tool. So it doesn't matter whether we have radial flow or linear flow. We make our pseudopressure and our pseudopressure derivative plots. And then I am going to insert a shape if I can find them. How come I can't find shapes? How do I move O? No? Spark lines? What are spark lines? How come I can't find shapes? Insert. What? Ah, shapes. Here's a line. Okay, now I got a line. Now to put half slope on here, I'm going to go over 2 and up 1, over 2 and up 1, over 2 and up 1. Okay, would everybody agree that that's half slope? And do you see that my derivative and my dimensionless pressure, dimensionless time both have half slope? So now we've diagnosed 3 things. What happened to it? We diagnose that we have some linear flow. I'm sorry, radial flow.
Why does it have a slope of a half?
What?
Why does it have a slope of a half?
You might remember very early on that I said the big difference between radial flow and linear flow is in radial flow we usually take the semi-log of our time axis. And in linear flow, what do we do with the time axis? Square root of time. And square root of time data plotted on a log-log plot will give you a log-log slope of 1/2. So it's related to that square root of time. So, and that's why our semi-log derivative is flat, because because we build in our log function into the semi-log derivative. We're taking the log of the time. Okay, so that's, by making the semi-log derivative, it's basically saying that if you plotted this on a semi-log piece of paper, you'd get a straight line through the data. So the derivative of a straight line is a constant. Okay? So this one curve basically is the whole course. Okay? Because it handles radial flow, the semi-log derivative, it also detects for boundaries, and it handles this linear flow situation. And the thing about that half slope is that both the p versus time and the derivative are half slopes. So you can expect those two parallel lines. And notice when I come back to my type curve that we have this telescoping thing of lines between the P sub d and the T sub d, and we don't ever have parallel lines between our derivative and our dimensionless pressure function. So there's no radial skin storage data before my radial data. So I go from linear flow to radial flow to boundary dominated flow. I actually have all that information knowing that, and this. Actually, even without the type curve, I can tell you right now that my early time data is linear. I have a transition into radial, and then I have a transition to boundary dominated flow. It's all in this graph. And this brings us back to the point of why I don't like the term middle time region. Middle time region was invented before we fracked wells. And middle time region represented the time after wellbore storage but before boundary dominated data. Okay? Now, if you like middle time region, where's the middle time region here? You see, I have two flow regimes that are middle time region. I have two flow regimes that are prior to boundary dominated flow and after wellbore storage. So the concept, the wording middle time region is leaving normal usage. Middle time region means you're looking at radial flow, because there's only one region between boundary dominated and wellbore storage, radial flow. But here's an example of where between the two you have both radial and linear. Oh, I wish I had a You're talking about here? You see one? I'm blind. This? There's nothing there. On the chalkboard tray? There's a magnet here. There's not one down there. I made a mistake and didn't bring one. No, not for that. Won't work on the whiteboard. The next teacher's going to get really mad because it won't erase. That's fine. I I know what to do here. I'm not going to panic. We have the textbook, right? There's a picture of this.
Here you go.
Thanks. Okay. As oh, look at this. So as we ended our radial flow thing, there's a discussion of linear flow, and I think there's the classic figures that were generated by Cinco-Lay. There's your middle time region. This is all radial flow still. There's a Horner plot. There's a horrible representation. Now we're into linear. No, we're not. Type curve matching, skin storage type curve matching. Here we go. This is what I wanted to grab. This is what I was going to draw on the board. So I don't have any markers here on my... Here, this is what's represented in the middle time region of our data. This is linear flow, C. And actually, anytime I say linear flow, I'm always talking about formation linear flow. Theoretically, there's this thing called fracture linear flow, but it's over in a few seconds. And then there's bilinear flow, and we can sometimes see that, and we will see that in some of our examples in this textbook. But this example right here, I am seeing C, D, and E. Remember, all my early data was two parallel half-slope lines. That's formation linear flow. And then I had a little bit of transition. That little bit of transition is sometimes referred to as elliptical flow. And then as my well looks smaller compared to the region of the reservoir that I'm draining, I would go into radial flow. The only thing that's not on this picture right here is boundary dominated flow. So once I see the boundaries of my reservoir, I go into boundary dominated flow. So we should be able to calculate perm from our radial flow analysis. We could calculate skin, but that's fairly meaningless. We'd really like to know what our fracture half length is, and we can do that from a square root of time plot. And once we have our fracture half length and we have our perm, then we can also calculate from our radius of investigation our drainage region. So we can calculate gas in place. Okay? Yes?
If you're drilling a vertical well, but you're not factoring that, but the vertical well is very close to a natural fracture, are you going to see the same thing?
No, you're not going to see the same thing. So what's going to happen when your flow regime hits into that natural fracture?
You'll get linear.
No, because your wellbore's not intersecting that. It's a ghost effect. It's a shadow effect away from the wellbore. You're probably not going to see something as diagnosable as what we're doing here because it's not at the wellbore. So if there's a separation between the wellbore and its fracture and another natural fracture or fault, now if it's a sealing fault, we'll see it as a no-flow boundary and we'll pick it up just like we're seeing here. The other thing I should note here is when we see an outer boundary, we don't really know if that's 4 walls to the room or 4 sides to the room or just 1 or 2. We normally don't. Now, there is some advanced techniques. Typically on a Horner graph, if you can see a doubling of the slope of the line, that's 1 boundary. There's an echo effect. And that means our derivative should be flat start to flip up, and then go flat again. There should be a second semi-log straight line. We don't have that in our data. So we're going to assume that it's a confining boundary all the way around, and we'll calculate gas and Blaise in that. If it did have that subtle lip and have a second straight line, which we'd see on the drawdown plot as well. Okay, I'm going to leave this book open. And you know, this might be where I lost my image last week. How do I get rid of this? Okay. I don't know how to get it back. There we go. Okay, so now let's crank out the analysis. All right? Let's crank out the analysis. We've already got a head start. I've already highlighted the data, time, and where our derivative match point slope is about 0.5, so we're going to want to plot pseudo pressure. Everything I'm highlighting in yellow should be part of my radial analysis. And we're already set up to do a radial analysis, right? This was borrowed from another problem, 6.32. Okay, I'm ready to change this. What is the number of the problem we're doing? 6.7? Okay, this is now officially 6.7 because all my plots and all my data are 6.7. So now I'm really doing 6.7. Now we have a slope, okay? We've already embedded. See, I'm recycling everything I've ever done. I've got a slope. Let's go see what it was grabbing. It was grabbing this data up here. It looks like I made a mistake. Oh, I didn't use pseudo time. I was using real time and pseudo pressure. Okay, that's delta pseudo pressure. I'm going to slide my pressure down to this range down here, and I'm going to slide my time down. And I'm going to slide my time over from real time to apparent time. Okay, so now I have a new slope. See that? And then those are already absolute. I'm going to copy it down, get the same number, change the spelling to intercept. If you have to crank out a lot of these during the day, you learn all these shortcut tricks. You don't start over every one. Okay, so I have a slope and an intercept. I wonder if I have an equation for a perm. I do. It's based on a rate of 300 MCF a day, that slope, that temp, that gas gravity, that H, and that's it. And I think I just need to add some significant digits here. Okay, 0.115. And the textbook has 0.0 something, doesn't it? What's the textbook have for this? That's 6.8. 0.088. Yeah, I'll leave this here. It's where is it? 6.7. Oh, right here. 0.088, just like you said. Okay, so they got 0.088, and I get about 20% higher than the textbook did. Keep it in mind, I didn't use their constants for viscosity and compressibility. I used my own calculations of pseudo time, And I know that I'm using a different correlation for viscosity than the textbook. Okay. Skin might be good. Oh, but see, I'm missing right in this cell, I'm missing a pseudo pressure I. I'm going to grab that because I have a pseudo pressure I. It's right there. And now I got a skin of minus 5.4 using my viscosity, my total system compressibility, my slope, and my intercept. And I've got a skin of minus 5.4, and the textbook has a skin of minus 5. Okay? I'm actually ready to make an estimate of my fracture half length. Okay? I'm going to calculate a fracture half length because I believe I have a fracture. Why do I believe I have a fracture? Huh? Because we got linear flow, so we got a fracture. So if I got a skin, I don't see it on my thing here, but, apparent wellbore radius uses my skin and my actual RW. See that? RW e to the minus S. That's my apparent wellbore radius. So it's seeing a 53-foot, it's acting like it's seeing a 53-foot diameter. Now, who has read ahead enough to tell me what my, by the way, the book uses L sub F. I'm always going to use X sub F. I don't know who switched to L sub F, but I don't like it. We like X sub F because when we're gridding our simulators, then we know that anything in the X direction's along my fracture length and anything in the Y direction's perpendicular to it, and so it's easy for my mind to be working with my grid cells if I leave it as X to F. Home, format, we're at font, subscript. So I'm going to say this X sub F, I want to add to this, from RWA Who can tell me what that is? Yeah, how am I going to calculate it? Equals what? X sub F divided by 2 is RWA. So it's equal to 2 times RWA. And that's only true for infinite conductivity.
Why is it double of the apparent wellbore radius?
What? It's RWA divided by 2? Is that what you just said?
No. Why is this so? Why is it double of this?
Why is what?
Why is it double? Why is it double your radius?
I think I'm understanding you. I'm using this equation right here. X sub F divided by 2 equals RWA. I mean, I didn't do the derivation for that, and so I don't have an answer for you. But that's the equation I'm using. For an infinite conductivity fracture, the fracture half length can be approximated by 2 RWA e to the minus F.
How do you know whether or not it's infinite or finite?
Those are good questions. Let's do that next. Let's get another type curve. Where am I? I should be in Let's get a finite conductivity fracture type curve. This is for constant rate, so that's a drawdown or a buildup. Okay, I normally grab my well or example name. Usually this is a well name. And I got to change 6.3 to 7.67 here in a minute. My X series is my T sub D, and I don't think this is going to be right. We're going to have to change this, I think, versus my P sub D. I have a T sub D X sub F. I don't have a T sub D over C sub D squared. So I have a different match point on my dimensionless time scale than I do on my pressure. My pressure scale is going to be the same because it's still P sub D. P sub D has the same definition, and let me restate that. P sub D has only one definition. Dimensionless time can be dimensionless time, T sub D over C sub D, or T sub D X sub F. Now, I really can't go from one to the other. I'm going to have to add a column and get a different match point for a different T sub D. What in the world happened to my oh, here it is. Let's put it first. So this is going to be T sub D X sub F. And I'm going to have some match point here that's different than the other match point because it's not going to be T sub D dash, it's going to be T sub D X sub F. And we'll start with 1. We'll set our time scale so it's that F4 times, and these two are interrelated, not necessarily here because we don't know C sub D, but if we did know C sub D, we could take out the C sub D and the RWA and put in the X sub F, and you could interrelate the two, times my TA. So that's in column G. So I move my time from H to G. And now I've got to fiddle with it until I get a match. I started with 1. Looks like it's got to be smaller. I should not have to change my P sub D to get on my type curve. Pretty close. I'm going to call that good. Can you see that? Okay, so here's my dimensionless fracture conductivity. Low, 1, 5, still low, 10. Most of the wells I see in the industry have a fracture conductivity, dimensionless fracture conductivity of 10. So when I run my numerical simulation models, I have to vary frac length and I have to vary the ratio between frac width, drainage radius width and distance. But so I don't have to run too many cases. I almost always run my cases with a frac conductivity of 10. There's analytic solutions for your frac connectivity of infinite connectivity. So there's a lot of solutions that they're dancing around for infinite connectivity fractures, like this one right here that relates apparent wellbore radius with skin. You kind of have to do a little bit more work when you're looking at dimensionless or dimensional or fracture conductivity less than infinite. And basically, when it's about 500, it behaves as infinite. And really, I'm not trying to match these first few data points because I'm going to run off my line up here, and I'm bounded up here by this line up here.
First thing we do is really put it on that tester and see if we have finite or
I'm going to answer that question even more fully. Typically, if you have finite conductivity vertical fracture, the first flow regime you see is not linear flow, but bilinear flow. Okay? So we're not doing chapter 9 yet, but when we do transient rate analysis, I'll probably give you a Barnett Shale example. We usually see 6 months. Here, these tests are in hours. We usually see 6 months of bilinear flow. And that's because instead of being 0.08 millidarcies, we're like 50, 100 nanodarcies.
bilinear when you only have flow coming into your fracture from like one area, not from both areas, or what is really principally bilinear?
Well, we had the picture up just a little while ago. Oh, here's a, oh, look at that. I'm going to get to bilinear flow in a second. Here's this relationship between frac conductivity and apparent wellbore radius. And you can see that line taps out at 0.5 for high fracture conductivities. I can actually, if you told me that my frac conductivity was 10 or some other number, I could actually come in here with any apparent wellbore radius and calculate the frac length. This is a very effective curve right here. Where's my single lay diagram? Here it is right here. So here's bilinear flow. You know, this is better than PowerPoint. Okay, there's bilinear flow. So we see, and actually the reason we see bilinear flow in the field is because of relative permeability issues. The Cinco-Lay original work on formation linear flow, bilinear flow, all of it was analytic. And when you're doing those analytic type problems, it's single phase, probably liquid. They may have ran gas. But in reality, 99% of our wells that we frack with water. So as soon as we shut off the pumps, our propped sand fracture is filled with water. And then what we're doing is, if you think about this from a secondary recovery aspect, we're gas flooding a water-filled frac. And so we're trying to get all the water out. And what do we call that in the field? Flowback. Okay, so we're trying to or clean up. We're trying to clean up and get our well to start producing commercial quantities of gas. The first thing that can come out of the ground has to be water. It has to be frac water because your frac is filled with water. Okay, then water production goes down and gas rate goes up, and then they start going their own way. So bilinear flow from an enhanced oil recovery mindset is I'm gas flooding a water frac. And so where do I flood that first? I flood it, see where the 3 arrows next to the wellbore area is? I'm flooding it first there because my reservoir sees the well as the largest, lowest point in pressure. So, and then as I flow in from the fracture into the wellbore, that leaves a lower pressure there, and so it starts drawing in gas. I'm using my fingers in the way that the figure is up here on the board. but actually it's like this in the ground. And if you were to plot water saturation versus time, your water saturation starts decreasing near the wellbore, and then it takes a long time to the term we like to use until the fracture tip ends are felt. That means we're completely gas flooded our water filled fracture, and we're no longer producing any water out of the frac. And we run enough, if you had a sand pack that was full of water and took it down to the lap and started running gas through it, the first thing that's going to come out of water is water, and after some point in time you're at irreducible water, and the only thing that's going to come through is gas. When you're at that point, you're out of bilinear flow.
So you're in linear flow whenever you're blowing back a well for any frac water, producing any frac water?
The first second when you turn on the well bore, you're in fracture linear flow. The only thing that's going into that well bore is out of the prop fracture. Think of the comparison and the permeability of a sand pack.
Yeah.
So that's fracture linear flow.
So bilinear is when you're draining both the fracture and the reservoir through that reservoir.
I like the enhanced oil recovery term. I'm gas flooding a water-filled frac.
Okay.
But because the pressure sinks in the middle of that sand pack, it floods from the inside out. It takes a long time for the tip of the fracture to be completely flooded.
Right.
But during that period of time where I got this perpendicular fracture linear flow and formation linear flow, we call that bilinear flow. And actually, I usually talk to people that in the industry that may not even be engineers, and so I don't usually use the term bilinear flow. Cleanup.
Can you see this in an oil reservoir?
Yes, every Barnett shale well has bilinear flow, 3 months, 6 months of it. It plots as a quarter slope.
But the Barnett's gas, or mostly gas.
Yeah. Oh, in an oil well. I think if I looked at an Eagle Ford, I could see bilinear flow. Not necessarily the Bakken. The Bakken has good permeability. You got to remember the Bakken's a special case. The middle Bakken is a true reservoir with permeability on the order of 0.02 millidarcies, not 100 nanodarcies. Okay? And then it is still self-sourced because the upper and lower Bakken are true organic shales. But if you ran a production log across the vertical section, nothing would come out of the shale. The shale sources the reservoir, and then the reservoir is what produces.
So it's really pure, like bilinear, you have to have two phases down there.
You have to have two phases. No, you don't have to have two phases. If I had a propane frac, and I had a propane reservoir, I'd still have bilinear flow. So I probably misled you with the whole mindset of that. You still have bilinear flow because most of the flow into your wellbore is right next to it along the fracture. And then it's being fed by the formation into that. It still takes time. It's seeing more and more of the fracture length as time goes on until, again, the fracture tips are felt. Once there's actually flow from the fracture tips, then you have this pure formation linear flow, and you're done with bilinear flow. But that period of time is greatly extended than that predicted by Cinco-Lay, because his work was single phase, because it was analytic solutions, and the simulators that we run, we now actually fill our reservoir, our frac with water, pump the typical amount that goes in, flow back the water, and we see that it takes a lot longer to get out of bilinear flow. When this paper first came out, we never thought we would see bilinear flow from production analysis. We thought we could see it in a pressure buildup because we had crystal quartz gauges and we could measure it at 100th of a second. Okay, we thought we could see it. This whole concept was developed because of crystal quartz gauges, and we could start measuring very accurate pressures at very early times. Again, this came out in the 70s. We never thought we'd see it in production analysis, but we didn't know that we would be producing from nanodarsy reservoirs And we didn't know that the permeability contrast was going to be so great between the formation and the fracture. Yes, just to feel the tips of the fracture. As you can see in this diagram, you're still flowing from the formation, but the percentage of the formation that's feeding the fracture, that's why as you move along the top, you got two arrows coming in next to the well bore, and then those get spaced out. But when the fracture tip is felt, and because the pressure drawdown in the fracture is so much lower than the pressure drawdown in the reservoir, you tend to have pure formation linear flow. When we get into Chapter 9 and talk about production decline curve analysis, that's the dominant flow regime right there. Formation linear flow. I'm glad when you guys ask questions, because those are the points I'm trying to get out from a conceptual basis.
I just have a very simple question. I think for the shale gas like Eagle Flow and the Barker, most of the flow are in formation linear flow. It usually takes 10 years or 20 years.
Yeah, I have a famous well called the Silkworth, that has been in linear flow for 20 years.
Yeah, so if the flow is linear flow, because it takes a really long time, so it's really very hard for us to do some tests in this flow region.
What?
I mean,
I love this flow regime. It tells you more than radial flow tells you.
in this region, can we measure the permeability and
If you only have formation linear flow, the answer is yes in multi-frac horizontals, because the fractures interfere with each other. When they do, they go into boundary dominated flow. And there's three basic unknowns: distance, time, and perm. I know how far apart I space my fracs. I can see on a decline curve analysis the time it takes for those fracs to interfere with each other. I get perm. I get a far better perm than I get in a Horner plot radial analysis. In a Horner plot, I'm only seeing a small bulk volume of rock. When I'm measuring the perm between 300-foot frac lengths that are parallel to each other, I'm measuring a very large bulk volume of rock. Average system permeability. I like the permeability numbers I get better from linear flow, and actually what I'm capturing is the end of linear flow. The end of linear flow, when it goes into boundary dominated flow, like this well went into boundary dominated flow, it goes into boundary dominated flow when we have two parallel fracs, the drainage radius gets closer and closer to each other. When they hit, then everything, all the pressures drop along that no pressure, no flow boundary halfway between the 2 points. I can calculate the distance halfway between. I can see from my decline curve how long that took, and I can calculate the permeability.
So you go straight from linear to boundary in that case, or you actually have this tiny infusion rate?
This is an important point. We never have D and E in multi-frac horizontals.
So you never have a elliptical
Correct.
pseudo rate?
Yeah. I've studied probably a dozen multi-frac horizontal wells, reservoirs. Barnett, Haynesville, Eagleford, Woodford, Bakken, Piance Creek, Niobrara, Montney. I will draw this on the board. Where did I get this marker from? You'll see this when we get to Chapter 9. My favorite plot is rate versus cume. And you'll get a straight line. And then you'll get a curve. It's reciprocal rate, so upside down this would look like a log-log type curve. Usually this is half slope, but because it doesn't intersect the origin, it's not exactly half slope. If it intercepts the origin, it's infinite conductivity fracture. So this intercept right here gives me the fracture conductivity. This slope, as we will see in this chapter, this is your half slope. Anytime we see half slope on a pressure buildup or on a decline curve analysis, it's telling us that we can get the product, the square root of K x sub f. We're going to get that in chapter 6 and in chapter 9. Anytime we got linear flow, we're going to get a straight line. Typically it's versus the square root of time. We'll always use square root of time in chapter 6, and in chapter 9 we're going to use cumulative production. I'll explain that later. But we're always going to get a straight line, and it's always going to be proportional to the square root of kxf. In production analysis, we will see this deviate and go north. Everybody knows what I mean when I say north, right? Because if you're looking at a map, you usually have the map north. I don't know. Everybody has GPS today. Maybe they don't know what a map looks like. Where it deviates, I can get perm. So now I got perm. If I got perm, I got the square root of perm. If I got the square root of perm, I can divide it into the square root of kxf, and I got xf. Okay? So this analysis, and we'll get it on this well's tonight's analysis, we'll first get K. We've already gotten K. It's what? 0.1, right? In production analysis, we got to get to this point to get K. We can't get it immediately. The same thing was true in this well. We didn't get K until we got done with linear flow. I'm not going to get K in chapter 9 until I'm done with linear flow and into boundary dominated flow. It's an after the fact calculation. But once I do, I've got K, I can get x sub f. And lastly, this intercept, both conceptually and calculatably, gives me my frac conductivity. So if you're a completion engineer, the most important thing to you is the intercept, because you're trying to improve frac conductivity. So you can measure your frac conductivity from pressure buildup analysis or transient rate analysis and figure out what jobs gave you what conductivity and try to optimize your frac conductivity. I think I'm still missing one point of your question. Oh, yes. If you go, and we can look at the type curves either in our textbook or in another one. I'm going to glance at see if we have ours. If you go from linear flow to radial flow through elliptical flow like D and E do, okay, this line breaks this way and then will come up. I think I saw the type curves here when I was passing through. I've got 40 years of professional history. I have never, ever seen a well break east rather than north. Never. Vertical fractures, it's easy to explain in multi-frac horizontals in a pattern. There's no place for radial flow to exist. But like I say, because we had a drilling boom in the Bakken over 20 years ago, and then no offsets were drilled, I got a vertical well, single frac, that only produces linear flow. There's no explanation why it doesn't go into pseudo-radial. It's not something I can explain to you mathematically. It has something to do with either the permeability anisotropy, the existence of leak-off fractures, or some other phenomena that prevents us from breaking east. But from a production analysis standpoint, I know what it would look like if it did have radial flow. And so the example we're looking at right now is ludicrous. It was generated from a simulator, okay? But I guarantee it's not an actual field example.
So, will multi-frac horizontal ever be in radial flow at the very end of it? Like, the whole thing, you know, like
All I can say, I'm shaking my head no.
You've never seen it.
I've never seen it. I've never seen anything broke east. Now, I'll show you this type curve. I think I've already flashed by it in the textbook.
Yeah, because I realize that the single stages could never be radial, but the well as a whole.
Yes. And you know what? Not everybody agrees with me. Yeah, make them a little bit bigger. See, I don't have anything in between. I'm pretty sure that I saw the standard transient pressure analysis. Here's the one we're doing right now. Here's the one we just matched for conductivity, but that was Cinco-Lay's, not Bennett's. I like Bennett's better. Here's the one I'm trying to show. Now, I'm going to lose this on camera. But it's one of the reasons I like this room. Now you got to find me a yardstick. Here's my log half slope that's also equal to my slope on my reciprocal rate cum. I'm trying to draw a straight line. Only on this type curve do I have a situation where it breaks north. Do you notice that all these other curves, here's kind of the end of linear flow. All these other curves go out of linear flow and into radial flow. They all break east. So once this line's started, it can be extrapolated, and there's only one case for a well breaking north, and that's a well with its boundary equal to its frac half length. If the boundary does not equal the half frac length, according to the theory, you should break east because you should break into some kind of radial flow before you see your boundary. So knowing this, and knowing that I've never seen a well break east, they all break north. Even vertical wells, where you should suspect after 20 years they should break into this. They only stay on this line or break north. I've never seen a horizontal well without a fracture. I know they exist in SAGD enhanced recovery projects, steam-assisted gravity drainage. We do drill horizontal wells, but they're usually steam injection wells.
I mean for oil wells.
Who has ever drilled a horizontal oil well? Who?
There are a lot of wells.
All of our wells are horizontal.
And you don't frack them.
We've never fractured a horizontal oil well.
What's your formation thickness?
150,
Huh?
150, 250, minimum 50. We get a very high permeability, like 300 milliliters an hour.
Why do you waste time drilling a horizontal well? Why don't you just drill a vertical well?
To save the cost and to maximize or escalate the production, because by drilling one horizontal well, you are going to save a lot of cost rather than a lot of vertical well.
What depth are you at?
10,000 feet. Between 10 and
Yeah, it's just not something that we have in North America. We don't have, you're probably talking about Darcy permeability?
we have that, but in those ones we have like 500, 200
200 millidarcy, yeah. We call that low-hanging fruit. And in our country, we've already picked the low-hanging fruit, okay? We probably still have some Gulf of Mexico wells that will still find with Darcy. I call it Darcy perm, but 0.5 Darcy's is still Darcy perm. Something that you're going to express in Darcy's. Okay, so I actually, until we had this discussion, I actually have never known of anybody that drilled a horizontal well without fracking it. So this is news to me. But I can see why, if you have enough perm, you don't have to frack, and you still have more exposure. But I'm really surprised, with 150 feet, you should be able to get substantial production rates. Now, if you have sand control and want to reduce your drawdown near your wellbore, a horizontal well may pay off that. Are you gravel packing them?
No, but most of them are carbon and footing.
Oh, okay. I can't tell you. First of all, you're asking an oil well question in a natural gas engineering class.
Yeah, but some of them like under the city, so and they have high.
There's, you know, we do this at the airport in Oklahoma City.
No, but you don't have
We
H2S, right?
what?
H2S. You don't
Oh, okay. So you're. That's another thing is you don't want to produce a well that has H2S near a population. So there are reasons for special reasons for drilling horizontal wells, but most of these people that are going to be practicing in North America, horizontal non-fracture stimulated wells are going to be an extreme rarity. And you sound like you already know more about it than I do.
I'll
Yeah.
ask the dumb question, being a guy not from petroleum engineering, but will you diagram what you mean by a multi-frac horizontal so I can visualize it?
Oh, I saw a great one today and I copied it. It was on Encana's website. I'm either going to pull up the original or I'm going to pull up a copy. Where is their fields or their fracturing? There's the picture I'm looking for. This is the one I saw today. Okay, it looks a little bit better in PowerPoint, but here's your drilling rig, here's your surface, here's your wellbore. It goes down and it turns horizontal at the kickoff point, okay? And then if you look at the blow up of the horizontal well in this oval right here, I can't get any. How come I can't? Yeah, there we go. Then along that horizontal, there's two primary ways to do this. You can do an open hole or cased hole. You can have plug and perf, which means we've got a cemented liner, or we can do a packer port system where we have swellable packers. This is what we do in the Bakken. And then we have ports that open up on mechanisms, And then we have, what we want to do is access and frack at places along the horizontal. Typically those fracks are 100 feet apart.
Are those fracks in line with the axis, or are they orthogonal? Or are they
Not always, but in general, you drill your horizontal orthogonal to maximum stress so that you have your fractures go perpendicular to your wellbore. There are some theories, depending upon the permeability, and it's said that for higher permeabilities, you want them parallel to your horizontal well, making kind of one big disc along your wellbore.
at least for modeling purposes?
Yeah, yeah. Yeah, typically, I've got them all, any work I do, my simplified model is just parallel fractures, just like if I was to take a bunch of pieces of paper and run a pin through them. Maybe I like that because it was kind of artistic. Anyway, multi-frac horizontals, covered in 48 seconds. Okay, any other questions while I'm on a roll? Yeah.
The permeability we got now from the slope of radial flow, there is a currently, right?
Mm-hmm.
Because we are only covering the slope of radial time region, so there's just a reservoir permeability. If we change the slope for the time till the flow is linear, would that permeability be for the reservoir, for the structure, any other permeability?
I'm probably not answering your question, but if this was a real situation, I would like this permeability better than the permeability I normally get because it'd be away from the wellbore. It'd be in that elliptical, pseudo-radial flow regime. It'd be way out there.
I did this by changing the slope. The permeability of reservoir is 0.1, and by changing the slope, the permeability of linear flow is 0.7, which is 800 times greater.
I don't know what you mean by change the slope. I only can find one radial slope, and that's where this derivative is.
If you find the slope of a linear time only.
I can't use that for radial. If my data points are not a semi-log derivative flat line, I should not be trying to calculate a slope. There are techniques that do a continuous derivative of all the data and try to calculate this permeability as you move away from the wellbore. I'm not going there. I'm just sticking with the tools that I have. There are more complicated tools, but I only use the slope to calculate permeability when I'm in a radial flow regime. What you're talking about is done by some people. Not me. Yeah.
For bilinear flow, is it a function of the reservoir permeability or the fracture permeability?
Both. I would have a hard time pulling up the Bennett paper, but on this graph that we're looking at right now, the triangles are the end of bilinear flow. And you see there is no triangle on the bottom line. The bottom line is very high conductivity. Very high conductivity means you don't have bilinear flow. The higher the conductivity, the less bilinear flow.
But by conductivity, you're referring to the conductivity of the fracture itself.
It's dimensionless fracture conductivity. Where did we get introduced to fractures? The original Cinco equation Now we use CFD. He used CR, and he has this term pi in there. But W is fracture width, typically about 1/10 of an inch. K is the permeability of the fracture. That's Darcy range. That's a sand pack. KF, K fracture. And then K downstairs is formation permeability, and LF is my XF, fracture half length. That's dimensionless conductivity. Okay, so we have low conductivity to high conductivity, and the triangles show the end of bilinear flow. So in our top curve, where our dimensionless conductivity is 1, here we're using even another symbol for fracture conductivity, sigma, but that dimensionless fracture conductivity is spelled out for us. The triangle's 2/3 along the line. If we come down 1, it's about in the same place, but when we come down to 10 for dimensionless fracture conductivity, it moves over considerably. When we get down to 25, more considerably. When we're at 100, it's almost off the graph, and at 500, there is no bilinear flow. The higher the frac conductivity, the less bilinear flow we have. Okay, so I think the original question, the reason we brought up this graph, someone wanted to know why it was infinite conductivity. But I'm glad we went to the textbook and showed how we could get an estimate. We can get an estimate of fracture half length regardless of the conductivity. But we now have a wellbore storage and fracture half length estimate, and we really haven't done any work tonight. We put a couple of data points, a couple of things on our graph with trial and error, and we utilize an equation that we already had for permanent skin when we did the radial section of our drawdown. Let's take a little break, and then when we come back, we'll do a square root of time plot and calculate fracture half length directly. I'm going to pause. The duration's changing. Okay. Any questions so far? We've got 3 graphs. We got a Bennett type curve, which is very useful in displaying our results in terms of fracture conductivity.
Where did you get this chart?
I got it from the spreadsheet that says type curves. I think I still got mine open. You guys got this. You got them all. Carter, Bennett. It's the same place we got the, and we're gonna use this one too. Let's get this one up here. Is this T sub D? Yeah. Let's grab this one next. You got a spreadsheet, right? This is where we got our skin storage type curve. Let's get, now we're on our type curve roll. Let's grab the Green Garden type curve. Now, notice the Green Garden type curve has the same variables, T sub dx versus P sub d. Do you see that? I don't have to make any new columns. I don't have to do any matching. I should be able to get my data immediately on the Green Garden type curve. Now, yep. I was trying to think of a clever way to get my data off the other one and put it on here, but I can't think of it. Okay, so we have T sub D, X sub F. For some reason, my X sub F didn't get subscripted. T sub D, X sub F, and we have P sub D. Notice on these linear flow type curves, I don't have any pressure derivative, but I don't really need one because for the most part, they're 1/2. But I'm going to put my linear one on for, I am actually going to do some work here. Okay. Select data. Did I ever change my name? I still haven't changed my name. I'm going to change that to 6.7 next time I remember. T sub D X sub F. We've already got that calculated match. I may even alter my match a little bit. And I always hit the delete key. I don't know why I have that default in there. And then my P sub D. I can't see which one is P sub D. There it is. It's column I. Okay. Okay. And voila. See, it was the same variable, so it should match right on there. And this is a type curve for the purpose of this type of data. Its data lasts a long time, 5,585 hours. I can't do this one in my head. It's almost a year. It's 232 days. So if you're going to see a boundary, there's a good chance you will. So you can see the latter point of the boundary start to crawl up that curve between 5 and 7 for a ratio of x sub e over x sub f. So that's the same boundary we saw in the derivative type curve. Okay? And here we can see some important things that might be helpful for us. It tells us when the end of the linear flow period is. That's good because I'm already guaranteed what data will I be able to use for a square root of time plot. I'll be able to use data prior to a T sub D x sub f of 0.01. I may have to change my pennies here. Now my rollover says why does it still say 0.01? Isn't that T sub D x sub f? I don't understand why that doesn't say 0.013. These rollovers should give me the same degree of accuracy as my I'm trying to find this point. And it's not giving me the same there I found it, 127. Okay, and this point right here I'm going to roll over is 01199. It's this point right here. So my linear flow period, why have I got this data highlighted? Should be this, should be linear flow. Let's get a different color. That should be my linear flow period. Okay, I think I'm done with this type curve at the time. See, I didn't have to make any adjustment to my T sub D to get it on my type curve. In fact, if I want to do anything, I might make a P sub D, but I like it when I don't have to change anything. So let's get this out of the way. Again, these type curves are really good for presenting your results. And with any of these matches, you can directly solve for those parameters. This was some kind of error formula. Okay, let's calculate fracture half-length directly using the books and the techniques in the book. Let's go ahead and copy our equation. oops. Summary of working equations, linear flow analysis, and hydraulically fractured wells. Pressure in time, pressure squared in time, adjusted pressure in time. None of those apply to me. And then finally we have summary of working equations, linear flow analysis, and hydraulically fractured wells. Pseudo pressure in time. That's what I want to see. Now, can I not copy paste? Now, you know what I did since the last class? I put my snipping tool here. Now, did we try this before? No, we did. We can't get that. Okay, well, we know how to do this. What's, Gene, what's my alt space bar? Voila, now I have equations. How do I crop this? Okay. Review, view, data formulas. How come? I think I'm only going to be able to shrink it. Okay, I'm going to want to use an equation to calculate the square root of kxf from the slope of a straight line. This is on a flow test, pseudo pressure versus the square root of time. I currently don't have a column for the square root of time, and I'm going to put that in. We're not going to plot any, well, we can plot 0. Okay, now I'm going to go grab some graph. This is left over from another problem. Don't I have, where's my drawdown plot? I must have at least had a drawdown plot. It doesn't appear that I have a drawdown plot. Okay, I'm going to copy this graph. Cut it. Get back over where I want to work. Expand. And paste. Okay, this is just some graph. But what we're going to plot now is pseudo pressure versus the square root of time. And it's not going to be log-log. Let me get rid of these lines. I'll leave one of them there since they're so hard to find. I'm going to get rid of my derivative curve. And, oops, I got rid of the whole graph. And I'm going to get rid of my log. And I want my array. I do this all the time. I just overwrite what I had on here. Although it's going to be a little difficult. But I like challenges. Okay, square root of time. I think I can even have my 0 point. Versus, comma, pseudo pressure. 8, 7, 6. I'm taking the square root of my apparent pseudo time. Okay, now I'm probably going to have to play with the axis mins and max. Okay, there's my data on my graph. And my early time data should be linear. It should be linear for the first, data points, the ones I highlighted. But there was this 2 highlighting issue. I think I highlighted these are the data points that should be a straight line. 1, 2, 3, 4, 5, 6, 7, 8, 9 data points. My first 9 data points should be a straight line. Bless you. Okay. And it doesn't look very convincing. That they're a straight line. So let's do a blow up. Let's get this out of here. I'm going to paste it twice. So I can blow this up for the first, I'm going to cut this back to 10. And then probably 2E8. Okay, let's see what this looks like. So here's my first bit of data points. Now it's a little more convincing that this is a straight line. And it's got to be a straight line. I got half slope. Remember, I've got half slope on my log-log plot and my log-log derivative, and I've done a type curve match, and my type curve match tells me that I should have linear flow. I got 3 reasons to believe, besides the fact that all of the data go through a straight line, that this is the slope that I'm going to use to calculate my fracture half-length. I'm actually going to calculate this coupled parameter, the square root of kxf, but I already got perm. I divide that by the square root of perm, and I'll have my fracture half-length. Okay, I got the equation. I am ready to go. I already have an equation that does slope, wherever it is. Probably covered it up. Here it is, slope and intercept. Okay, that's my radial. Incidentally, like I said earlier, you're never going to see a buildup like this or a drawdown like this because I've never seen one. one that has both radial and linear flow. I want to put it right next to this. I got to be careful what I move. So now we're going to do linear flow. Slope and intercept. Here's the slope equation. Let's see what it grabs and move it. Remember, it grabbed the late time data. So let's come back up here and grab the early time data. Pseudo pressure. And this is time. But I don't want time. I want the square root of time. So now I'm going to have the slope of the pseudo pressure versus the square root of time for the first 1, 2, 3, 4, 5, 6, 7, 8, 9, and I think that's exactly what I wanted. 1, 2, 3, 4, 5, 6, 7, 8, 9. I got a 10th point. If I was to actually do this, I'm going to use 0. I can't always use 0, but I'm going to use 0. Okay. Now I've got the slope. I did something wrong. Oh, I got to get rid of the log. I get rid of some of these extra parens. And then I am going to copy that down and change the spelling of slope to intercept. Another reason we can determine that we have infinite conductivity, and like I said, the reason I used that original point, I really shouldn't have. Now that I know what I'm doing, I really shouldn't have used my initial point. My initial pressure of 5,000 pounds, it's pseudo pressure at time 0. I shouldn't have used that because you may have an intercept that's different than your initial pressure. Let's see what pseudo pressure that is. Equals pressure 1 that's pseudo pressure at this reservoir temperature, this gas gravity, that nitrogen, that CO2, and that H2S. And this is how I know that this was data came from a simulator with infinite conductivity fracture. The backcast of the early drawdown data actually exactly intercepts 5,000 psi, or the pseudo pressure that's associated with it. Typically in a drawdown, your intercept will be slightly different than that, and that's due to finite conductivity. So you can actually calculate your conductivity even if you don't have bilinear flow based on that difference in intercept. But I did correct a thing. I really want to go from 7 to 15, not 6 to 15. Okay, and I'm getting very, very close to the initial pressure. So that's the intercept of my early straight line matching the actual known value there tells me that I have, is another indication that I have infinite conductivity. Okay, now we calculated perm. Let's calculate KXF. And I think we'll quit after we do that. So here's my equation for KXF. I'm trying to get it in the right place. I'm not doing a very good job. Yeah, here we go. You know, can I use my snippet tool here? Ah. You know what? That would have worked if I would have just slid this graph over and I could have gotten that exponent. Let's try that one more time. Now I just have to hit paste. There we go. So let's do this. This is all we're going to do tonight. Now, do I like that equation? Well, we know what our answer is, right? It's a 70. What was our? We should get 107. Well, after we get whatever we're going to get, then we're going to get our fracture half length. Equal to the square root of KXF, which we're about ready to calculate, divided by the perm raised to the 0.5. This is going to give me 0 right now. But hopefully after I calculate this square root of KXF, I'll get a number of about 107 feet. So let's see if this equation works. Equals 40.93 times our gas rates, 3,000, times our reservoir temperature. And who asked me the question by email about Fahrenheit and Rankine? Okay. If you see T in any of these equations, it's asking for Rankine. Okay? So every time I've done this in class, I've always typed in open a paren and did 460 plus, because we display our temperature in degrees Fahrenheit. Okay. Divided by the slope. Well, we've already calculated the slope. It's right here. Divided by H. Then it says times 1 over that, but how about if I just divide by that grouping? Divide by porosity times gas viscosity times gas total system compressibility. I think I'm done. Oh yeah. There is. Can I get away with just putting it right there? And the answer is yes. I think 129 is fairly close to my 107 for my frac half length. I don't think I have to. No, because the square root of 1 is 1. That's fine. Okay. So I finished. I haven't calculated my drainage area. But what I would do there is, let's do it using our type curve. Instead of using our radius of investigation, let's utilize our type curve. We have a type curve that, our Greengarten type curve, we should display our slope on these graphs. Let's use our Gringarten type curve. Is there anything else we want to do with that? I think I'm done with that. Let's see if we can't use our Gringarten type curve to determine our drainage area. This is just one of two ways to do it. Okay, 1.5, 2, 3, 5. It's starting to travel up the stem based on my match here of an x sub e over x sub f equal to 1. Here's x sub f, and here's x sub e. And are we a square? I think we're always a square. Area equals 4xe squared. Do you see that? Right on my type curve. It tells me how to calculate my area. I have x sub f. Now I have the ratio of x sub f to x sub e. X sub e is all I need to know to calculate the area. Let me double check. 1, 1.5, 2 is the number on top of it, 5. X sub e over x sub f equals 5. That tells me that x sub e is equal to x sub f divided by x sub f over e. Is that right? No. Times it. Is that? I think I got that backwards. These are families of x sub e over x sub f. I put this in upside down. There we go. So x sub e is x sub e over x sub f times x sub f. So my x sub e is 5 times 129. $647. My area, just like it says on the type curve. My area is 4xe squared. Remember, this test almost lasted 2 years. And that's in square feet. So my gas in place, since this is an original one, we can do original gas in place, is equal to, do I type in 43560? No, because I'm already in square feet. Times SG times phi times H divided by B sub G. Am I missing anything? That'll give it to me in standard cubic feet. Let's divide it by 1,000, because the minimum unit we ever use is MCF. Seems like I made a mistake here. And normally when we talk about reservoirs, we talk about BCF. And so I'm going to take another million off of that. And that's a commercial reservoir. 2.66 BCF. Except for the fact that this is synthetic, and I've never seen a pressure transient analysis go from linear flow to radial flow. This does depict everything that you might want to do with linear flow, except for the fact that we have limited ourselves with the Greengarten type curve to what conductivity? Infinite conductivity. The Greengarten type curve, when we look and try to plot finite conductivity on the Greengarten type curve, we'll have a little bit of problem. But I think that's a good place to end tonight's work. Question? Which one? I can't hear you. XE. XE is X sub F times XE over X sub F. Okay? See how the X sub F's cancel? And you end up with XE. The X sub E over X sub F I picked out on the family of type curves. That's what my data was climbing up the X sub E over X sub F of 5. My X sub F I calculated as 129 feet. So I multiply those two together and I get X sub E of 647 feet once I get rid of the pennies. Mm-hmm.
For the TD curve, TD square curve, what data you use? You use PD or use PP or I mean the curve you build for the PP and square root?
You know what? I might have used delta PP and I might have used Emma P. It wouldn't make any difference. It wouldn't make any difference. Because one just has a constant subtracted from it, and I'm looking for a slope. I probably use delta P because it's a positive slope. But remember, I already built in there, remember that my slope has the absolute value. If I would have taken pseudo pressure, I would have been a negative slope, but I would have still pulled out the absolute value. Wouldn't have made any difference if I used delta pseudo pressure or pressure. I mean delta pseudo pressure or pseudo pressure. I'm going to cut off the recording. I could have approached this problem a number of different ways. I could have just rushed to judgment, got a square root of time, plot built, and gotten square root of KXF first. Saw that it ended, looked for a later radial flow period, gotten perm, and then finished everything. Put my presentations done last. I kind of tried to bob and weave and do things a little